In the last video, we learned how to perform Gaussian curve fitting in the beam viewer environment using a sample entry spot from 150 MeV starshot. In this video, we learned how to use differential weighting to correct Gaussian fit of an exit beam spot with a probe BB aberration. So I'll load up the exit spot from the same beam. Now this starshot was delivered at 145mm Z, actually aimed at the probe fiducial BB. So when you look at the exit spot, you can see the beam passed over the probe BB, which is a high Z material and was scattered. So there is what looks like a shadow in the exit beam spot. When we look at the Gaussian fit of this data, you can see it's not very good. A sigma measurement taken from this fit would probably not be very representative of the actual beam. Ideally, we recommend that you aim away from the probe BB, like at reference hole G, if you want to perform the best profile measurements on exit spots. But all is not lost. Basically, we can use these weighting tools to discount the error from the central region to achieve a fit that represents the actual beam. Empirically, we found that setting the measurement bars to intersect the data at the FWHM, or the 50% intensity level, worked well. So the template does that automatically. Actually, it sets the bars to the beam diameter, which is the average of FWHM measurements taken at 72 different profile orientations. So maybe you just need to adjust them slightly for a given profile. Then we select the tails only weighting preset. If we scroll down here, you can see that in the central region, there is no contribution to the error. The optimizer just ignores those data points and converges on a distribution which matches the tail regions of the data. Now let's resolve the fit. You can see the sum of square error drop dramatically from 30,000 to about 300, and the sigma change from 4.8 to 4.2. So what's the rationale for recommending this correction method? We had several data sets where the same beam was delivered with and without a probe BB in the way, and we know some things about how entry spots should compare to exit spots. For instance, the entry to exit ratio for beam sigma was about 93% on pristine beams, and this correction produced an exit spot sigma which maintained that ratio. We were also able to verify the amplitude or the height of the fit. Peak intensity can be checked by multiplying the peak percentage of the fit, about 110 here, by the max gray value. And when we carried that through, we found it yielded a grayscale value very close to that of the exit spot of the pristine beam. Again, we recommend if you want to measure very precise exit spot profiles, don't target the probe BB, but you can see this is a nice little tool for manipulating the curve fit if you do have strange exit spots, and it may be useful to you. And when you're closing this template, if you do want to save the fit data, just make sure that you hit Save As and give it a new name so you're not overwriting the blank template, which is going to be accessed again by the Beamworks software. In the next video, we'll look at the Excel analysis export option, which is similar but provides a higher level, more comprehensive view of the beam spot.